For example, you can define separate functions for arm, waist, and shoulder calculations in individual script files, such as sleeves.py or waist.py. These functions can then be imported into a central Python script, like garment_design.py, where they are combined for broader use. This setup allows you to call specific functions, such as sleeve calculations, without needing to process the entire garment logic every time. However, the method of organizing and accessing these files depends on your overall project structure and tools. For instance, while garment_design.py can serve as a Python-based directory for combining logic, the directory structure itself could just as easily be SQL-based or another system entirely, depending on the storage and access requirements. Accessing these directories or functions introduces another layer of complexity. For example, if you're importing functions at a later time, you might do so via a database that stores function names, parameters, or paths. Alternatively, you could use the Python console directly to import and call specific functions. The design of this workflow will depend on whether your priority is real-time accessibility, dynamic updates, or integration with external systems. Creating the directory itself is a separate step that involves thoughtful organization of files. If you're working with Python, you might create a structured folder with submodules, or if using SQL, you might map out a schema where each table represents different garment components. This organizational phase is critical for ensuring the modular design works efficiently, whether accessed programmatically or manually later. So, while breaking functions into modular Python scripts is a good approach, the full context involves considerations around directory structure, tools, Python versus SQL or others, and how those functions are accessed or reused across different stages of the design process. This modularity provides flexibility but requires careful planning for seamless integration across the system. In programming, there is a concept called the DRY principle, which stands for "don't repeat yourself." This principle encourages modular programming to minimize redundancy. Modularity can be useful depending on the project's scope, complexity, and the extent to which functions need to be reused. For instance, in a garment design project, modularity might be beneficial when calculations or components, such as a sleeve module, are reused across multiple designs like shirts, coats, or dresses. As a designer, one might decide to create a reusable module, especially when designing a collection where consistent style is desired across garments. A sleeve module could ensure uniformity in sleeve design across different items, while also making it easier to expand functionality by adding features like fabric stretch calculations, seam allowances, or custom measurements. Modular code has advantages, such as being easier to debug and expand. Long, monolithic scripts can be difficult to manage, whereas breaking functionality into separate files improves readability and allows multiple people to work on different parts of the project simultaneously. However, modularization may not always be necessary. For small, one-off projects or designs with highly unique requirements, a single script might suffice, and creating modules could be excessive. A hybrid approach can be useful when unsure about the extent of modularization needed. This involves starting small by combining the DRY principle with a pragmatic structure. For example, you might create modules for shared logic, like a measurements.py file for utility functions, e.g., converting inches to centimeters, rounding values, or validating inputs, or a constants.py file for shared constants like fabric shrinkage rates or seam allowances. Specific calculations, such as those for sleeves, can be isolated in their own module. For example, a sleeve module could handle calculations for sleeve length, cuff width, and fabric stretch, making updates or debugging specific to sleeves more efficient. By isolating logic, one can save it as a .py file and import it into other parts of the project as needed. This ensures changes to one part, such as updating the cuff width formula, automatically apply wherever the module is used without affecting unrelated code. Additional features, like tapered or flared sleeves, can be integrated into the module as the project evolves. For instance, parameters or new functions can manage slight variations required by different garment types, all while keeping the module reusable and independently testable. Unit testing can be performed on modules to validate their behavior before integrating them into the larger project. For example, a test for calculating sleeve length might assert that the function produces the correct result for given inputs. This approach ensures accuracy and reduces the need for retesting unrelated parts of the project. Specialized logic for specific cases, like asymmetrical sleeves or variable seam allowances, can also be housed in the module, making it easier to add or modify features over time. The importance of modularity becomes clear when considering its role in automation. All the calculations and designs discussed are eventually translated into instructions for a machine to produce the garment. Once the software has the full set of garment measurements based on customer inputs and design parameters, it can communicate with the actuators and mechanisms of the manufacturing machine to execute precise operations, such as cutting fabric or sewing seams. This integration highlights the practical value of modular, well-organized code in streamlining design and production processes. Modern software like Cloud3D, CLO3D, Marvelous Designer, and Browseware offer advanced 3D simulations that incorporate pre-built libraries with physical properties for various fabric types. These tools enable designers to create highly realistic garment simulations, allowing them to visualize how different fabrics behave in virtual environments. By leveraging these predefined fabric properties, designers can simulate real-world behaviors such as draping, stretching, and movement, without the need for manual calculation or testing. This functionality streamlines the design process, enabling faster prototyping and more accurate representations of how garments will look and fit in reality. Such software tools are especially useful in industries like fashion design, where accurate fabric simulations are critical for ensuring that the final product aligns with the designer's vision and performance requirements. When it comes to the machinery we're designing, I've already discussed in my tech farming videos that Fusion 360 is a great alternative to SolidWorks due to its affordability. There are other tools available as well, such as Aura Atom 3D and various design software, but Fusion 360 stands out as the best. Additionally, MATLAB is a valuable tool for integration with Fusion 360 and Python. Now, when it comes to the prototype of the mechanical system, we will obviously be working with a scaled-down version. It's simply not feasible to build a full-scale machine, especially for someone like me. Before you even think about building anything, however, meticulous planning, mathematical calculations, and designing are crucial. According to what I read in my textbook, about 80% of the total project cost is in the design and planning phase. Getting this phase right is essential, particularly when you're working with a scaled-down prototype, as it helps save a significant amount of money on materials. Everything is prototyped and simulated using tools like Fusion 360, MATLAB, and even Python. The benefit of this approach is that you're proving your understanding by going through a detailed process. It's similar to what architects do. They create miniature models to demonstrate their expertise before constructing a full building. This is how I approach building my portfolio in engineering and robotics without having to spend years getting a degree. I believe this method allows me to save money while still gaining the necessary education and experience to pursue a career in the field. It's a solid approach. Building a scaled-down prototype of a machine or robotic system is not only a valid approach but also practical and efficient, particularly when full-scale models are too costly or resource-intensive. While this method introduces certain challenges, such as the nonlinear scaling effects, these can be addressed with careful planning and mathematical modeling. By working with miniature versions, you reduce material, fabrication, and component costs. Additionally, you can validate design concepts, test mechanisms, and identify potential issues without committing to a full-scale build. Smaller models allow for faster iteration, enabling you to refine your design before scaling up. Even though there are scaling effects, proper adjustments, including accounting for forces, vibrations, and load effects, allow for the effective testing of mechanisms and kinematics. This is why topics like calculus and trigonometry are so important. I use examples like cars, which are complex mechanical systems, to understand these concepts in a practical way. If I can grasp the mechanics of cars, I'll be able to better understand how to apply trigonometry to robotics and mechanical systems. However, there are scaling challenges to consider, such as nonlinear scaling effects where mass scales with volume, and forces like gravity remain constant. This results in frictional forces disproportionately affecting smaller models, and miniaturized materials may not behave the same under load or vibration as their full-scale counterparts. Resonant frequencies and damping effects also differ with scale. To account for these differences, you use mathematical modeling and apply principles of dimensional analysis, which predict the performance of the full-scale system based on scaled data. Scaling laws help adjust for forces, vibrations, and load effects. In the design process, it's essential to ensure kinematic and dynamic similarity, meaning the motion paths and forces, such as inertial, gravitational, and damping forces, should be proportional between the prototype and full-scale system. Simulations, using tools like Fusion 360 and SimScale, can replicate full-scale conditions even for smaller prototypes. You should also use materials with properties similar to the full-scale system, lightweight but stiff for structural elements, for example. While it might not always be feasible to use steel or metal for every component, plastic can be used for non-critical parts, with the more important structural mechanisms made from metal. In terms of scaling forces and vibrations, it's important to adjust these parameters in testing calculations based on the scale. For instance, if a prototype is half the scale of the full model, dynamic forces scale as 1/8, while mass scaling follows the same ratio. Stiffness may scale differently, so it's critical to focus on the most important subsystems for the overall performance. In complex systems like mine, which will feature multiple subsystems such as actuators, sensors, and load-bearing structures, it's essential to prioritize modeling these critical components. If the full miniature build becomes too complex, creating test rigs for specific functions, like joints and actuators, can be an efficient alternative. Using off-the-shelf small-scale components like micro-servos, miniature gears, and linear actuators can save time and resources, rather than building everything from scratch. By gathering data from these prototypes, you can refine your mathematical models to more accurately predict full-scale behavior. Building a scaled-down machine can absolutely work if approached thoughtfully. The key is acknowledging the scaling differences and compensating for them through careful calculations, simulations, and material choices. Even a miniature prototype can provide valuable insights and reduce the risk in the development of full-scale systems. When embarking on a project that involves creating machinery or structural components, designers must navigate several challenges, including the costs and complexities of fabrication, the scalability of designs, and material choices. This essay explores key considerations for cost-effective design, including the importance of off-the-shelf solutions, alternatives to metal fabrication, and practical methods for accessing specialized steel fabrication tools. One of the most critical aspects of design is ensuring scalability, which directly impacts cost, accessibility, and feasibility. Scaling a model down to smaller dimensions often allows for the use of off-the-shelf components. For instance, proportional design, smaller scale models typically require less powerful motors, bearings, and other components, making it easier to find readily available and cost-effective parts. Commercial availability. By leveraging existing products, designers save time and avoid the expense of custom manufacturing. Off-the-shelf screws, bearings, and motors are often standardized, ensuring compatibility with other parts and reducing the risk of errors in assembly. Cost savings. Off-the-shelf components streamline the procurement process, allowing designers to focus resources on other aspects of the project. However, scaling comes with challenges. A miniature model might restrict the strength or durability of certain components, requiring innovative solutions like alternative materials or custom fabrication. While metal is a preferred material for many applications due to its strength and durability, it poses challenges in terms of cost, weight, and fabrication complexity. To address these issues, engineering plastics and composites are valuable alternatives. Nylon, Delrin, acetal, and UHMWPE, these engineering plastics are ideal for parts requiring wear resistance, low friction, or high impact tolerance. They are widely used in conveyor systems, gears, and grinding components. Fiberglass reinforced plastics, FRP, offering excellent strength-to-weight ratios, FRPs are suitable for load-bearing applications and are often used in structural components. Cost and manufacturing benefits. Unlike metal, these materials are easier to machine, mold, or cast, reducing the need for specialized tools and lowering production costs. By integrating alternative materials into the design, engineers can achieve the required functionality while minimizing fabrication challenges. Metal fabrication often requires specialized tools such as CNC machines, welders, plasma cutters, or water jet cutters. These tools are typically expensive to purchase and may not be readily available through general equipment rental outlets like Lowe's or Home Depot. To bridge this gap, designers have several options. Companies such as Sunbelt Rentals, United Rentals, and Red Deer specialize in industrial equipment rentals, offering tools like welders, plasma cutters, and other fabrication machinery. Suppliers like Airgas, Praxair, and Matheson Gas often rent welding equipment, torches, and plasma cutters. Community workshops like Tech Shop, Maker Labs, or Fab Labs provide access to CNC machines, 3D printers, and welding equipment. These spaces are ideal for small-scale projects or prototyping. Many machine shops allow designers to rent time on equipment or pay for custom work, such as cutting or forming steel. Platforms like Rentals.com or Zillow occasionally list specialized equipment for rent in specific locations. Alternative and/or hybrid approach, outsourcing. When renting or purchasing equipment is not feasible, outsourcing fabrication tasks to local shops or specialized services can be a practical solution. Fabrication shops, local steel fabricators can cut, weld, and form components to specification, often at a lower cost than in-house work. Waterjet and laser cutting services. These services provide precise, custom steel parts without requiring the purchase or rental of machinery. The ability to scale and adapt designs often depends on the accessibility of materials and tools. By integrating off-the-shelf components, alternative materials, and strategic outsourcing, designers can create robust and cost-effective systems without overextending budgets or resources. For example, using engineering plastics like Delrin or UHMWPE for components such as bearings and grinding parts reduces the need for welding or machining metal. For load-bearing components, fiberglass reinforced plastics offer a lightweight alternative that retains strength. When steel is unavoidable, outsourcing or renting specialized tools ensures fabrication is completed efficiently. Designing machinery or structural systems requires careful consideration of materials, scalability, and fabrication methods. By leveraging off-the-shelf solutions, alternative materials, and accessible fabrication options, designers can overcome challenges associated with cost, complexity, and time. Whether through renting equipment, outsourcing tasks, or integrating innovative materials, the goal is to create functional, scalable designs that align with budgetary and practical constraints. This comprehensive approach ensures that projects are not only feasible but also optimized for performance and affordability. The intersection of technology, mathematics, and practical problem-solving offers us a pathway to solve real-world challenges with elegance and precision. One such challenge is body mapping, creating an accurate, digital representation of the human form for applications in fashion, fitness, healthcare, and beyond. While some propose high-tech solutions like bodysuits with nanotechnology fabrics, a simpler, more cost-effective, and precise alternative lies in the power of mathematics, particularly trigonometry and parametric modeling. Trigonometry, the study of the relationships between the angles and sides of triangles, is a cornerstone of geometric modeling. In the context of body mapping, trigonometry enables the creation of a digital mesh, a network of triangles that approximate the contours of the human body. Triangulation is the process of dividing a complex shape or surface into smaller, manageable triangles. Each triangle is defined by 3 key points, nodes, and their connecting edges. This approach is foundational because triangles are inherently stable. Unlike other polygons, a triangle's shape is determined completely by its side lengths and angles, making it ideal for modeling. Precision through small segments. By breaking down curves and irregular shapes into many small triangles, the resulting mesh captures the body's nuances with high fidelity. For example, a curve along a body part, such as an arm, can be divided into small arcs. These arcs are approximated with straight-line segments that form triangles. By measuring the lengths and angles at each node, the mathematical relationships defined by sine, cosine, and tangent functions allow us to calculate precise positions in 2D or 3D space. To model more complex, curved features of the body, we turn to parametric equations. These equations describe curves and surfaces in terms of parameters that vary continuously. For example, a wave-like muscle contour can be modeled using sinusoidal functions like y equals a sin, bx plus c, where a controls amplitude, height, b determines frequency, tightness of waves, and c sets phase, horizontal shift. Circular arcs, such as those found at joints like elbows or shoulders, are represented using x equals r cosine, theta, and y equals r sine, theta, where r is the radius and theta, the angle. These equations allow flexibility. For irregular or asymmetric features, the radius, r, or other parameters can be functions themselves, varying dynamically to account for irregularities. Parametric equations extend naturally into 3 dimensions. For instance, the torso, which resembles a cylinder, can be modeled as x equals r cosine, theta, y equals r sine, theta, z equals h. Here, r is the radius of the torso, theta is the rotational angle, and h is the height along the z-axis. Variations in r or h can create the irregularities necessary to match real body shapes. Mathematical modeling and trigonometry offer several advantages over hardware-based solutions like bodysuits. 1. Precision without physical limitations. Physical devices like bodysuits are constrained by material properties such as stretch, tension, and elasticity, which can distort measurements. In contrast, mathematical methods are immune to such inaccuracies. By relying on direct inputs, such as photographs, key body measurements, and traceable contours, mathematics ensures unparalleled precision. 2. Cost-effectiveness and accessibility. Bodysuits embedded with nanotechnology are prohibitively expensive to produce and purchase. Meanwhile, mathematical approaches require only basic tools, such as a camera or measuring tape, and accessible software for processing the data. This affordability democratizes the technology, making it available to a broader audience. 3. Adaptability and scalability. Mathematical models can adapt to any body type or feature. Complexities such as asymmetry or unique curves are handled by refining the equations or increasing the resolution of triangulation. Updates to the model can be implemented via software changes, which is far easier than redesigning hardware. 4. Sustainability. By eliminating the need for physical materials, mathematical methods reduce environmental impact. Bodysuits, with their reliance on advanced materials, contribute to waste during manufacturing and eventual disposal. 5. Integration with automation and AI. Mathematical systems are naturally compatible with automation. AI can further refine curve detection, optimize triangulation, and account for irregularities in real time. This integration paves the way for software solutions that surpass the capabilities of any physical device. A significant strength of the mathematical approach lies in starting with simple base shapes. For instance, the torso might initially be modeled as a cylinder, and limbs as truncated cones. These base equations provide a foundational framework. The parameters, r, theta, and h, are adjusted to reflect true body measurements. Additional functions are overlaid to account for irregularities, such as muscle contours or joint protrusions. This stepwise refinement ensures that the final digital model mirrors the unique geometry of the individual while maintaining computational efficiency. The use of functions like r equals f, theta, to define variable radii or irregular shapes demonstrates the creative potential of mathematics. Unlike traditional problem solving, where equations are chosen to fit predefined scenarios, this approach highlights how we can invent equations tailored to our need. By combining trigonometric, polynomial, and parametric functions, we gain the flexibility to model virtually any form. This adaptability underscores the power of mathematical thinking. It transforms abstract principles into practical tools for real-world innovation. Choosing between hardware-driven and software-driven body mapping underscores a larger truth: technology must be both effective and accessible. The mathematical approach not only meets these criteria but exceeds them by offering a scalable, sustainable, and precise alternative to hardware like bodysuits. By embracing mathematics and trigonometry as tools for body mapping, we open doors to new possibilities. Affordable digital tailoring and custom fashion. Improved prosthetic design tailored to individual anatomy. Enhanced healthcare diagnostics through precise body modeling. Through automation and AI integration, these methods promise to revolutionize industries while empowering individuals to engage with technology in meaningful ways. Body mapping is a trigonometric endeavor, and its most efficient realization lies in mathematical modeling. By leveraging principles like triangulation, parametric equations, and creative problem solving, we can achieve precision and adaptability far beyond what physical devices like bodysuits offer. More importantly, this approach democratizes access, making body mapping a tool for everyone, not just the privileged few. Mathematics isn't just an abstract discipline, it's a practical force for change, capable of reshaping industries and improving lives. In body mapping, it proves that the simplest solutions are often the most profound. eShakti, ESHAKTI, and similar services can only go so far with standard measurements because they are working within the constraints of pre-designed garments. They essentially tweak the size and length of the dress based on a customer's provided measurements but do not fully repattern the garment to accommodate unique body shapes. This is a key limitation of their model, even though it offers a more tailored fit than off-the-rack clothing. The issue lies in the lack of a comprehensive approach, such as using 3D body modeling to create fully customized patterns. Measurements like bust, waist, and hip circumference only provide a limited snapshot of a person's shape. They don't account for proportions, posture, or unique body characteristics, such as the width of shoulders, the tilt of the pelvis, or variations in torso and leg length. Without this detailed understanding, the fit of the garment can only be approximated. In contrast, using the approach we have been discussing would allow for a truly custom fit, as it would generate a complete digital model of the body. This could then be used to create patterns that account for all individual nuances. However, implementing such a system is currently expensive and logistically complex for mass-market clothing brands, especially those with moderate pricing. This is what for MV Morse aims to revolutionize and address. It's an interesting problem that highlights the gap between affordability and true customization in the fashion industry.